Swayam Prabha. Digital India. Educated India.
Okay, so essentially we have to compute the so-called posterior predictive distribution rather than just the predictive distribution. That is where things become a bit interesting, because if you let's go back to the previous case where we had kind of a limitation, right? Because when we were computing the predictive distribution, I just want to contrast this with the Bayesian approach that we are going to take, right? So in the case when we had MLE or map estimate, we could not do any averaging. We only had to rely on a single weight, weight vector, WMLE or W map, to make the prediction. So our predictive distribution had a certain mean, but a constant variance, because we were just using a single weight vector. But now we have the luxury of using the entire distribution in making the prediction. So how do we do that? Let's look at the posterior averaging. Okay, so we can now compute the posterior predictive distribution. So the goal is to use the entire posterior over W to make predictions, which is basically predicting Y star for a new input X star. Okay, so how does that happen? Well, the idea of posterior averaging, right? So we want to compute the posterior predictive distribution of Y star given X star, but not using any specific W, but all possible Ws. Okay, so we can always compute P of Y star given X star. I think I have a superfluous comma, so this comma should not, well, no, I think this is superfluous anyway. So this is like P of Y star given X star comma W comma beta. Okay, this is nothing but a Gaussian distribution, right? Our likelihood model already says that this is a Gaussian distribution. The second term is a posterior distribution, right? Which we have already computed. We already have the expression for this posterior distribution. But the important thing here is that we are not making this prediction using a single W, but we are actually making this using every possible W and averaging over all these possibilities. Yeah, it's a good point. Well, the thing is, nevertheless, mean is only a single point, right? So, well, average of all the Ws, right? But it's not necessarily the average of the predictions made by W, right? So if I have the distribution over, posterior distribution over W, right? Mean is only the average of W, right? But here we are computing a prediction. We are averaging a prediction, right? So if you think of, okay, so once we have the posterior distribution over W, we can say that the average W is the mean, right? But we can't say the same for the prediction, because the predictions, you have a linear kind of you have W transpose X, right? And you have a distribution and you are averaging an entire distribution, right? Rather than just averaging a bunch of weights, right? So, this is the proper way of doing it, right? So all you do is basically compute this prediction, but multiply it by the posterior probability of the corresponding, the W that you're using, and you do it with every W, okay? So this is the yeah.
So like instead of first averaging all W's and then calculating prediction,
Yes.
first calculate prediction for all W's and average that.
Yeah, so which is basically what we are doing here. But okay, so the thing is, how many possible W's you have? You have infinite many W's, right? Right. So which is why you have to do the integral, right? Now, in some cases, as I said, this integral operation is not always possible in all models, right? So in models where this is not possible, you actually do that. What you do, you actually sample a few W's or few parameters. You compute the prediction using each parameter and then do an empirical average. But here we are more lucky. We actually can do it in closed form, okay? Because this is Gaussian, so this integral is actually available in closed form, okay? Okay, so as I mentioned, both the terms in the right-hand side are Gaussian. The first term is nothing but our likelihood model, Y star given a normal distribution is Y star given W transpose X star and beta inverse. Second term is the posterior distribution that we just derived. It has a certain mean and a certain covariance matrix, okay? Now, answering your question, right? So if you only use the mean, you are anyway ignoring the covariance matrix, right? So the mean does not capture the uncertainty. And even intuitively, just using the mean does not, incorporate all the information. Averaging, because then the uncertainty will be incorporated in the averaging, because you are now relying on the full distribution, right? Rather than just relying on the mean, because if I just look at the mean doesn't have a notion of how spread out the distribution is, right? So which is why this is the full proper way of averaging that we are doing here, okay? So anyway, so both these distributions are Gaussian. Thankfully, this integral is available in closed form. Okay, and I'll just give you the. Okay, so I will not do the derivation here. Again, the derivation is a bit complicated. Okay, but I just want to give you the main insight as to what and that's that. And the insight is that you can actually do this in closed form, and it has a closed form solution. I'll just show you the solution and the significance of the solution, and that will tell you why averaging helps in cases like this. Okay, so the result of this integral turns out to be a Gaussian distribution with mean being mu transpose x star, where mu is the mean of the posterior distribution. Okay, mu we already computed on the previous slide, and the variance of this Gaussian distribution is beta inverse plus x star transpose sigma times x star. Okay, note that x star transpose sigma times x star will be another scalar number. Okay, so this is a column vector, this is a matrix, this is another column vector, right? So, so the posterior predictive distribution of y star given x star after averaging all possible values weighted according to the posterior distribution will be this Gaussian distribution. So the posterior predictive is again Gaussian. Note that it was Gaussian in the MLE case as well, or map case as well, but the prediction, the variance was just beta inverse, which was kind of disconcerting because it doesn't even make sense. Why should I have the same variance for every data point, right? Here, note that the variance does depend on x star, right? So for different inputs, I will have different variances, okay? Also note, yeah, so now answering your question, right? So you said that why can't I use the mean, right, to make the prediction? In fact, I am making use of the mean here. So the mean of the distribution is actually mu star times x star. Sorry, mu transpose times x star, right? But the variance, so yeah, so your intuition is correct, right? So I can just use the average mu and use it to predict, right? But we are not predicting a single value. We are looking for a distribution, right? Now, the mean of that distribution can indeed be mu star, and in fact, it turns out to be mu transpose x star, right? But we are also interested in the variance, right? And that is where the covariance matrix comes into picture, okay? This point can be slightly subtle, so if you have any questions, it's important that we clarify that before we move on, okay? But again, the basic message here is that we are able to, once we have the full posterior distribution over the unknown, which is W here, we can now do this posterior averaging, okay? Which is a benefit that is not there in the case when we are doing MLE or map estimation. Even though MLE and map are probabilistic approaches, due to the lack of averaging, they can be prone to overfitting because they just rely on a single prediction. But here we can have a more robust prediction, right? And we get more, intuitive estimates of the uncertainty, right? Because as you can see, the uncertainty in the prediction of a new input, in the output of a new input, it does depend on what the input is, rather than being the same, beta inverse for every input. Okay, so again, the mean is. So once you have found the posterior distribution over W, which is normal with mean vector mu and covariance matrix sigma that we already saw the expressions for in the previous slide, you can compute the predictive distribution for any input where the predictive mean will be mu transpose x star and the predictive variance will be beta inverse plus this additional term x star transpose sigma times x star. And just for comparison, I have mentioned the predictive distribution when we use MLE or map estimate, right? So there are two differences, right? First difference is that if you compare, so in the MLE predictive distribution, the mean is W MLE transpose x star, where in this case you have mu transpose x star, okay? Variance is just beta inverse, okay? Whereas here we have beta inverse plus this additional thing. Okay, so another point that is important to see why this makes sense. So in some sense, if you compare how much variance we have in the prediction, so MLE kind of underestimates the variance, right? So it says that the variance is just beta inverse, whereas the full averaging tells us that it's beta inverse plus some other positive number. And why does it make sense? Well, it makes sense because we are uncertain about W. So our predictions should also, so that uncertainty kind of percolates into the predictive distribution of Y as well, right? So in some sense, the MLE prediction and map prediction is overconfident, right? But once we also take into account the uncertainty in the W estimation of W, that uncertainty kind of translates into the uncertainty in the predictions, right? Which is why we have this additional factor of x star transpose sigma times x star, okay? So So it basically it's important in two ways. First of all, now the variance is input dependent. The other is that the variance is more as compared to the MLE variance, and it makes sense because we are the W itself is uncertain, right? So uncertainty in W translates into uncertainty in the prediction. In the MLE or map case, there is no uncertainty about W, right? Which is why there is no factor associated with that part. Okay, so I think that is the point I was making. Oh, yeah, one other important aspect about this posterior predictive distribution is that now that we have the uncertainty in the prediction dependent on the inputs, we can see which inputs are going to be more useful, right? So suppose I have a bunch of inputs, right? And I can, and suppose, and for each input, I can predict how much is the prediction as uncertainty, right? So I can see which inputs are difficult. For difficult inputs, the variance will be so like this quantity will be large for difficult inputs, right? So I can see which data points are difficult, which data points are easier. Okay. And so this picture kind of illustrates this idea of posterior predictive distribution that, if you suppose you have these black dots as your, points for which you are trying to fit a linear regression model, this black line is the predictive mean. So this is like the mu transpose X line. Okay, so this black line is mu transpose X. And this shaded region is basically the variance you have for different inputs. So as you can see, different so x-axis is this is the input, this is the output, and as you can see, this the variance is like slightly smaller in this region, but as you go to away from the data, the variance increases more and more. Okay, which kind of makes sense because in regions where you have a lot of data, the prediction can be more confident. But as you move away from the data, right, your model becomes more uncertain, your predictions becomes more uncertain as well. Okay. So this is not a very a representative picture, but typically I think I showed one picture in the very first lecture where we had a non-linear model, right? So there the idea was more clear. I'm not sure if I have another picture to illustrate the same thing. Okay, so any questions on this? Yes. 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 And exactly, and that's like it's needed because rather than being overconfident our prediction that my prediction y star is this value, why not report the confidence? I think my y star is this, has this mean and this variance, right? The other thing is this notion of active learning or sequence. So suppose I have trained a model using this much data, but suppose someone tells us that go and acquire some more data, some more x and y pairs, okay? So x comes for free, right? But y doesn't come for free, right? So what we can do, we can look at some of the data points, right, where I think y has a large variance, right? And we can say that let's incorporate those data points and retrain our model, right? So I mean, there's no point acquiring data points where my model is already fairly certain, right? So which is the notion of active learning or sequential data acquisition. So, well, okay, so that is the point, right? So suppose, okay, so I'll give you a simple example of spam classification. So it's not regression, but classification, right? So suppose, you're trying to learn a spam classifier, and you have a model like this where you have the confidence in the prediction of the label, right? Now, different emails. So if there is an annotator who labels every email as spam or not spam, right? So without showing it to the annotator, if I can somehow get a sense of how hard an email is to basically to predict whether it's a spam or not, right? So we can make that decision even without looking at right? So we can definitely get X. Getting X is kind of free, right? But it's getting the Y that is expensive, right? So rather than taking random X's, right? Why not take those X's that are hard and then give those X's to the annotator who can annotate that, right? So if annotation is expensive, why not spend our effort on the hard cases rather than easy cases, right? Right. So hopefully okay. So we are still doing linear regression, right? So we started with the linear regression problem. We said that we'll formulate it as a probabilistic model. So someone asked, okay, why bother about doing this in a probabilistic way, right? Hopefully it's clear as to what are some of the benefits. For example, this kind of a thing is not possible with a linear regression model, right? You can't get uncertainty estimates in your prediction or even in your weight vector, right? So whereas we can get clear uncertainty estimates in this case, right? And I did not talk about many of the other things, which I think I'll very briefly talk about some of the other facts that are useful with, yeah.
We were able to do all this given the prior
Y-
situation that we have.
Yes, yes.
So in case we don't have that,
Yeah.
this is not possible.
Yeah, so you can't do that easily. So I mean, you need to have some prior. Now the thing is, the prior doesn't have to be you can even like use some sort of a uninformative prior. So I said that you can use a Gaussian prior, right? But with some, so typically you can always assume that it's a zero mean Gaussian prior. It's a very reasonable kind of assumption, right? Yeah. Well, so the variance can be learned, okay, right? So the prior has a precision like lambda, right? So you can actually learn lambda. I'll show you how you can do that. I'll not go into the details, but you can, again, do a maximum likelihood estimation for lambda also, right? So that's the more important. I mean, this is one of the important aspects that you can get the estimate of uncertainty. The other benefit is that you can actually learn all the hyperparameters in the model. Okay, which is again not possible if you are just using a standard linear regression model, because there you have to do cross-validation to learn the regularization constant. There is no prior, right? But you have the lambda there also, right? In the L2 regularizer, right? So you typically have to do cross-validation to learn lambda. Here you don't have to do that. You can just like perform something called a marginal likelihood maximization, which will give you lambda. I'll very briefly talk about it in the next slide. Okay, so let me do that. Okay, so hyperparameter estimation is the next thing that I wanted to talk about. So in these problem setting that we discussed so far, we assume that W is the only unknown. Only the weight vector is unknown, and we assume that lambda and beta, the hyperparameters of the model, they are known. But there is nothing that stops us from estimating these if we are taking a probabilistic approach. Okay. And we don't even want to use cross-validation, because cross-validation is easy. You don't need a probabilistic model. So one way to solve for the hyperparameter or learn these hyperparameters is the idea of marginal likelihood maximization, which is something that I very briefly talked about in lecture 1 also. So the idea is that we can try to find the optimal lambda and beta by maximizing something called the marginal likelihood, which is the probability of y given the hyperparameter. Okay. Note that there is no W here. Okay, so I have integrated out, so in fact I have mentioned it right here, right? So this marginal likelihood is basically the likelihood with W integrated out, okay, with respect to the prior distribution. So this quantity can be computed, and this quantity will be a function of lambda and beta. Okay, so this is just some likelihood, but it's not in terms of W. W has been averaged over. It's only in terms of lambda and beta, right? So this is nothing. Think of this as the probability of y as a function of lambda and beta. So what will be the optimal lambda and beta? Well, the ones that maximize this probability, similar to a maximum likelihood estimation, right? But it's called maximum likelihood estimation of type 2 because this is not actually a likelihood. This is a marginal likelihood because we are integrating out W and we have this probability of y only as a function of lambda and beta. Okay, so this is one way of estimating the hyperparameters. Again, the technical details are a bit involved, which is why we are not talking about it. But in principle, you can estimate the hyperparameters using this MLE2 approach. You can even put prior distributions on these hyperparameters, and you learn those as well. There are lots of algorithms that you can use to basically learn these hyperparameters. So yeah, so that's another benefit, that if you have hyperparameters in the model, like linear regression, you can estimate those. Okay, so we restricted our discussion to linear regression, but you can fairly easily extend these models to nonlinear regression as well. Have you already seen kernel methods? Kernel methods have been right. So okay, so the thing is, the idea is that suppose I have data that looks like this. So this is clearly not, I can't fit a line on for this data. It will be a very bad fit, right? So I want to learn a model that looks something like this. I want to learn a curve, right? It turns out that there are, so we can use the same ideas that we saw earlier to learn curves like this. This can be done in many ways. One way is to map the data to a higher dimensional space. So I think I'm talking, so kernels, I think kernels were listed as one of the topics. So have you seen the idea of like taking data and mapping it to a higher dimensional space where things become linear? Okay, so the same idea, right? So you can so for example, suppose I have features as X, I can apply some nonlinear mapping, right, in the high dimensional space, right? So rather than treating our features as x, I can represent them as phi of x, right? Phi of x is some nonlinear representation of the features. And in that space, I can learn a linear model. Okay, so that's one way of doing it. So it's also related to the idea of kernelization. So these models can be kernelized fairly easily. I actually have a couple of slides after this slide on how to do kernelize it, but it's slightly, some of the details are slightly non-trivial, which is why I'll just show you the slides and then I'll stop. Okay, but anyway, so the idea is that if you want to do nonlinear regression, you can apply the same tricks that you have seen for kernel classification. Another way that you would become basically more, that you'll appreciate more after you see neural networks is to say that we can have our likelihood model P of y given x comma w as again a normal distribution, but the mean, instead of being W transpose X, let's make it the output of a neural network. Okay, so neural networks are nonlinear function approximators that take as input as something, and then they produce a nonlinear transformation, right? So so all I need to do is I can take the same approach of Gaussian likelihood model, but simply replace the mean by a nonlinear function that can be modeled by a deep neural network. So rather than using W transpose X, I can have a multi-layer perceptron, right, with lots of parameters, and then the goal will be to learn those parameters, right? So the training of the model is slightly more tricky, but the basic ideas and principles remain the same. Okay. So there are many. So the basic idea is that you can still, if you're doing nonlinear regression, probabilistic nonlinear regression, all you have to play with is the mean, the way you model the mean. Okay, so rather than saying that the mean is just W transpose X, either you write it as W transpose phi of X, where phi of X is some nonlinear mapping of the data, or you write the mean as F of X, where F is some nonlinear function, which is maybe defined by a deep neural network, and learn the parameters of the deep neural network using backpropagation, whatever you'll see after a couple of days, I think, deep neural nets. So this can be done, this can be extended to nonlinear settings as well. Okay, so the next slide, I don't want to scare you at the end, but basically there's something that you should maybe look up. So this is called, again, if you have seen kernelized SVMs, so there is a way to do probabilistic linear regression in a kernelized setting, right? Where the basic idea is that, if you are doing regression, if you have, in regression, the likelihood is Gaussian, right? So the basic idea is that rather than assuming that you have a model of the form y is equal to F transpose, W transpose X, you simply say that y is F of X. Just that, right? And one of the nice properties, so now what happens is that you can assume that the joint distribution, this probably would not make sense at this point, but I'll just mention it anyway, okay? So this is the last bit that I wanted to talk about. So the basic idea here is that if you have n training points, right, you can define a joint distribution over the outputs of those inputs as a Gaussian distribution in n dimensions, okay? So if I have n data points, so the outputs, I can say that, well, let's assume that the outputs are jointly distributed according to a Gaussian distribution with some mean and some kernel function, similar to the kernel function that you might have seen in SVMs, where each entry of the kernel function measures the similarity between two inputs. And one of the nice properties of the Gaussian distribution is that if you assume that this is true for the training set, and if you want to extend it to the test set. So what is this related? So I'm saying that the outputs of the training. So for the training data, the outputs are distributed according to Gaussian. So if I add the output of a test example here, right? I get from an n-dimensional Gaussian to an n+1 dimensional Gaussian. Okay. Now, so the joint distribution of the training outputs and the test output is Gaussian. Will also be a Gaussian. Okay. Now, Gaussians have this nice property that if the joint distribution of two sets of variables is Gaussian, then the distribution of one set conditioned on the other set is also Gaussian. Okay, and that's a very a nice idea which allows you to basically use the idea of kernels to do nonlinear regression. So this is like a very fascinating topic. Personally, I find it very, very appealing. So Gaussian process for regression, you should look up. The idea is that the distribution of the output of the test examples given the outputs of the training examples is again a Gaussian, whose mean and covariance can be obtained in closed form. And one of the good things about this approach is that you again get variances in the prediction. Okay, so that's you can always do nonlinear regression using kernel methods, but you won't get the uncertainty. But if you use something like a Gaussian process, you actually get all the benefits of a probabilistic or Bayesian approach, where you actually get uncertainty estimates about the predictions. Okay, so I think that is where, and yeah, so the nice thing is that you actually can learn nonlinear. So this picture kind of tells you the power of this nonlinear Gaussian process regression model. So you can learn nonlinear functions along with the uncertainty estimate, right? So as opposed to just nonlinear regression where you can just learn the curve. So all the benefits of probabilistic modeling that we talked about for the linear case, they naturally extend to the nonlinear case if you use something like a Gaussian process regression, or if you simply parameterize the mean of this likelihood model using a neural network. So then also you can actually learn the same kind of behavior. Okay? Yeah, so I think I would stop at this point. Any other questions? Okay.